Let me see. Oh God, it went into some strange mode. Do you see anything?
Let's see. 1 second. Also sending the reminder now.
Maybe.
Not yet.
Okay, so it's stuck there. Maybe you take control of the screen again and give it back to me or something.
I don't think it has that, but let's see. Like, this is what happens when I do present my entire screen. You can also try window or tab. That might be less complicated.
So can I quit and join again?
Try that. Sometimes it's a permissions thing. We have to restart.
Yeah.
All right, let's try this again.
Okay, I will see your entire screen.
Worst case, you can send me the slide. We can do it that way too.
Allowed to share screen, or should I say allowed to share window or screen? You know.
Let's try screen. I mean, it's you're allowing Chrome for the future. I think that's how this works.
Oh, this is okay. This is okay. Do you see anything?
Oh, I see something good. It's definitely your desktop. Somebody's desktop. I'll say that much.
Okay.
Yeah, and I think with PowerPoint definitely you have this special the presentation mode in a different window, so screen is probably the safest.
Okay, let's see. Can you see anything?
Perfect.
Okay. Good.
Okay, nice. So let me so yeah, we'll do it. I guess people on this call can always, I'll record this now, so I'll start the recording, and people on the call can ask questions live, and then people can also bug me offline, and I'll ask on their behalf as well. 1 minute, let me start the recording, and I'll just give you a really, really brief intro once it dings. 1 minute. Ooh, 1 second. I have to restart because my recording is not working. 1 second. All right. Hi, everybody. I'd love to introduce Rao Kotamarthi from Argonne National Labs, and he leads, one of the world's premier climate modeling groups. Welcome, Rao.
Yep, thank you. So one of the things I need to tell you before is that when I go on full screen mode with this presentation, I cannot see any of you. So if you have a question, if somebody
Don't
has
worry,
to...
we'll bug you.
Yep. So this is, I'm Rao Kotamarthi. I work at Argonne National Lab, as I said before. So many of you probably don't know what Argonne National Laboratory is, unless you're around Chicago area. It is established in 1946, and actually the first director of the lab was a guy named Enrico Fermi, who made the first sustainable nuclear reaction under tennis court in University of Chicago. So they thought, okay, this doesn't look too safe for a city, and they moved it outside the city, far away from the city, which was about 30 miles from the city. So that's where we are, Argonne. We are west of Chicago, about 30 miles. Right now, of course, the suburbs are all around us, and we are not anymore in a remote area, and very, very little of nuclear research goes on here in terms of doing actual nuclear power plants, but we do a lot of modeling and developing new areas of developing nuclear power within the laboratory. So We have a bunch of current one-of-a-kind facilities at the lab. One is the advanced photon source, which is right now going through an upgrade, essentially about probably a several $100 million upgrade. The idea is that this is one of the world's most powerful X-rays. People who do like X-ray crystallography, looking at protein structures and all, use this a lot. I think it was very helpful with the COVID-19 finding vaccines and stuff like that. There are other things where the one that is of most interest to me is the Argonne Leadership Computing Facility, which is a hosted computer called Theta, which is about 33 pflops right now. And we are on the verge of getting the next higher scale system called Aurora, which is expected to be up to more than an exascale. Maybe it will hit 2 exascale. We don't know yet. So that should be coming online in another few months. It has been like that for a while, but we have been assured that it will be end of the summer, it will be operating. The other thing that we closely work with is called atmospheric radiative measurement, our program, and we operate at several sites, which this is one of the oldest climate kind of a monitoring facility within the United States. One is in southern Great Plains, Oklahoma, which has been operating about 30 years. The idea is that you take a grid cell of a climate model, which used to be around 300 kilometers when it started, and populate it with a whole bunch of instruments to understand how it varies, how a particular variable will vary within the grid cell. Right now, the climate models operate around 100 kilometers, so the site has now become more dense around 100 kilometers. We also have about 6 other such facilities around the world, and Argonne operates a few of them. So why are we here? So this is the part I like to start with. This is the climate talk, and always good to talk about climate when trying to understand why the climate is changing. If you look at the carbon dioxide, which is the primary greenhouse gas concentrations, you can go back to about 800,000 thousands of years before. 1950 is the baseline here. What you see is that the current CO2 is about 420 ppm. It actually crossed that recently. This is about 2 years old. CO2 has never been increasing at this rate in recent history. You can go really way back and to get to numbers like this, but this has never been this high in about 20 million years. So this is a drastic change. That is, one thing is the change is happening. You may say that, okay, it might have happened before. There could be carbon dioxide levels at this scale once before in the human, not the human history, the history of the planet. But the rate of change we are observing, that's a rapid increase, has never happened before. So that's one of the concerning things, and how you can deal with this abrupt kind of very rapid change in climate that's going to happen. It's happening, and it's going to happen as we go forward. So what has already happened? If you look at the figure all to your left, what on my screen and hopefully on your screen, what it shows is the temperature change, observed global surface temperature change relative to 1850 to 1900 as a baseline. So you use that as kind of it's potentially you can call it pre-industrial. It is not exactly true. You have to go a little bit further. But looking at 1850 to 1900 as your baseline, what happened is that the current world global surface temperature is about 1.26 degrees centigrade. This is 2020. I think we are getting pretty close to 1.5 degrees. If you have heard a lot of discussion on the media about 1.5 degrees centigrade, 2 degrees centigrade, the Paris Agreement and things like that. The Paris Agreement initially thought 2 degrees centigrade would be a good thing. Then they revised that thing and said that actually optimally we should be at 1.5 degrees C change in surface temperature as soon as we can by 2030. I think that was the goal. And it doesn't look likely that we will meet the target. We probably will be crossing 1.5 degrees centigrade by 2030 based on the amount of activity that is taking place right now in reducing the primary emissions and things like that of carbon dioxide, which will go to a little bit in the next slide. So why do we believe that this change in temperature is occurring? Because of human, essentially us introducing fossil fuel, use of fossil fuel and greenhouse gases into the atmosphere. So I'm a modeler. I kind of trust the models to do saying these things. So if you do a modeling starting from 1850, and you only include natural variability like solar and volcanic, you get, if you look at the figure on the right, the color, kind of the blue color, shows you where we should have been, around plus or minus 0 degrees, pretty close to where the natural variability should be keeping us. But if you include in the same models the greenhouse gases that we have emitted into the atmosphere over the past 200 years, essentially, what you get is what we are observing right now. So that you cannot get this result by using natural variability in the climate. You have to include this anthropogenic kick that we are producing in terms of greenhouse gases into the atmosphere to get to what we see right now. So this is a kind of, so why do we believe in this model or any model at all? So this model produces what we have observed historically pretty well. It's not like a one-to-one match. I mean, it's not like a zero difference between the observed climate and the modeling. But the errors are pretty small. It shows the same kind of trend as we observed naturally over the past 150 years or 200 years. So we have a lot of confidence in these models, and the kind of things we are looking at, the kind of perturbation needed to get the temperature to what we see right now, it's definitely due to anthropogenic or human emissions.
So question on that point.
Yeah.
You're focusing on the atmosphere, but some of the temperature, change is being mopped up by the oceans, for one thing, as well as acidifying the oceans. So to what extent is that a phenomenon?
Yeah, that's a good question. So when we talk about a global surface temperature, like the average temperature, so 70% of the planet is oceans, right? So it is the average measured on the surface of the oceans. It's not the ocean water temperature, but just about the ocean and the land surface. So it's the average of the entire planet, not just the land atmosphere, it's for the entire average. So acidification is another, so some of the CO2 is the major sink for CO2 is oceans. So that as you increase more and more carbon dioxide in the atmosphere, some of it transfers into the ocean. At some point, you get actually saturated. Right now, we are not there yet, but it's as CO2 goes into the water, and you start acidifying some of the water. So those are also concerns as we go forward. So I hope I answered your question.
Yeah.
So what can we do? So if the climate is changing, we can give up or we can try to find a solution. So the first one we focus on is something called mitigation. What is mitigation? So if you look at all the emissions from various industrial sources on a global scale, what we see is that the power industry produces about 31% of the entire greenhouse gas inventory, essentially what we are emitting into the atmosphere. And there are other industries. This is kind of a lot of people forget. There are a lot of industries like cement. When you make cement is basically calcium carbonate, right? So when you make cement, you're emitting huge amounts of carbon dioxide in the atmosphere. Steel making, you use a lot of fuel to make steel, right? All these things actually emit about 19% of the greenhouse gases that we observe in the atmosphere, or increase we are seeing on the planet. So what we need to do is trying to figure out how we can reduce these emissions. Actually, it is pretty challenging task because you're thinking about a big.
Can you use that credit? Yes, say yes. Okay, just say yes, you can use the credit card.
Sorry, something about a credit card. We are working from home. So the industry is about 20%, and the industrial processes like steel and all produce a lot of these things. It's very hard to decrease carbon emissions from these sources. Buildings produce about 8% of the emissions. So what do you mean by buildings? Buildings are essentially like heating and cooling, direct energy related. So when you heat your house with burning natural gas, for example, you are directly emitting carbon emissions into the atmosphere. Then there is transportation, which is about 17% of the total emissions. So this is where all the electrification, electric cars and all are focused right now to reduce this transport-related emissions to as small as possible. So if you look at these numbers, it's about, even if you're the US, it's about slightly higher. It's about 20% of the total emission. So you're not just have to focus on this transportation sector, but you have to look at all other things. Ag and land is about 17%. So this is essentially the people using agriculture for various purposes, digging the soil to emit carbon and things like that. So it is a sobering thing when you look at this whole list of things. So how much needs to be done in different sectors? Right now, we are mostly focused on the power sector, where we are trying to introduce renewable energy and transportation sector. So that both together, probably you can see up to 50% of the emissions are there. So there is another 50% emission that a lot of people are not paying attention to, and we need to reduce that to zero. So the goal is when you hear a net zero by 2030, 2050, you're thinking about all these things. So what can we do is the next thing. So we can mitigate. We can also adapt. So what is adaptation? Adaptation is trying to understand a risk climate poses to our to a infrastructure, where we live, anything of critical importance to us. So when you think about risk, you are thinking about hazards. In this aspect, when you're talking about climate, you're looking at climate-related hazards. The second thing you are thinking about is vulnerability. So what is vulnerability? Vulnerability is an interesting concept, or it's easy to understand when you think about it like this. So let's say you have an earthquake of 6.0 Richter scale on somewhere in Japan, Tokyo, and compared to somewhere in Bolivia or some other country which doesn't have the resources. So the population in the poorer countries are much more vulnerable than the one in Tokyo, because they have taken the effort to make their infrastructure resilient to this kind of change. So they are less vulnerable compared to a different country which is in a poorer neighborhood, right? So that's the kind of thing we are thinking about vulnerability. So that you have a capacity to withstand a hazard, you become less vulnerable. And the final thing is exposure. Let's say you have a really big hurricane somewhere in the middle of the ocean. The exposure to human population, businesses, etc., is zero, right? But the same thing happens somewhere in Florida. The losses could be huge, and somewhere on a small island, it could be different, right? So that's the exposure risk. So the risk, essentially, when you're thinking about climate, is the combination of these three factors. And understanding risk helps you where I need to adapt. Adaptation is very expensive. For example, if you want to adapt to climate change in New York, and so that it doesn't flood, and build a wall around it, so I've seen estimates of some people about $10 billion to $20 billion, right? Not that you want to do that, it's just that if you want to do something like that, it's very, very expensive. So there is an idea of, if I want to adapt a small installation to some coming change, how much money do I want to invest? Where should I invest? And what is the risk for me for doing this? I'll show you an example of a nuclear reactors in a little bit. The last thing we can do is intervene. This is an interesting concept. This used to be on the edges of science. It still is. A lot of people are not very excited about these kinds of ideas. But there are several ways you can intervene globally to cool the Earth. Essentially, these things called radiative forcing geoengineering, or SFIs, people call them, trying to put mirrors or aerosols in the stratosphere, so you reflect some of the incoming radiation back to the space, so that not all of it reaches to the Earth. The three ideas shown here, for example, one is so-called marine cloud modification. It's on the right. So marine clouds are actually, there are huge decks of clouds that are around 30% of the planet that kind of always there. They have a really long lifetime, and they reflect a lot of their energy back. So the idea is that, can we make them more reflective, so they reflect more of the energy of the incoming radiation back, so that it cools some of the overall budget. And the other things are like putting sulfate in the aerosol. So whenever you have a volcanic explosion, for example, it has been established that the Earth actually cools by some degrees. We know if you think of volcanic explosion as an experiment, we have experimental proof that actually it reduces the surface temperature. But do you want to do that? If you want to do that artificially, then you have to pump these aerosols continuously into the stratosphere all the time, all the way, all through the year, blah, 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 right? It is going to be super expensive, and also we don't know the consequences of doing this on a regular basis, and what are the environmental impacts, who will be affected more, and things like that. There are other things like carbon dioxide removal, like you heard of carbon capture, and some of this new people have been trying to suck carbon out of the air, so-called direct air CO2 capture and storage. There are a few plants going up all around the world, and I think this is where Bill Gates is putting some of his money in, thinking about putting DAX. But this is, again, this could be doing this on a global scale it requires a huge amount of effort to scale these things to a level that actually will impact carbon dioxide levels in the atmosphere, and it will be super expensive.
So question about the effect, the effect of these approaches. Ignore cost for now, but if you change reflectance of the Earth, is that, I mean, it seems like it's you change the constant amount of temperature without changing the rate of increase of temperature, right? So it's a more of a, as I understand it, like you buy yourself a decade or two.
Yeah.
Is that the dynamic of that one?
Yeah, I mean, that's what. So there are a lot of nuances in what people are talking about right here. So, for example, their idea that the marine cloud brightening may be a regional thing, like you only do that over Arctic or somewhere, so that you can actually cool that place down and not there while we fix the other problems. Yes, it is. These are not like a permanent solutions, except for the carbon dioxide removal ones, which are more of a permanent. The solar radiation impacts changes are not permanent. It's supposed to be a short-term solution, short-term meaning decades, several 20, 30, 40 years, while we reduce the carbon in the atmosphere. But unfortunately, the challenge is that we even don't know how well these things work to apply them on a global scale or even on a regional scale. So that's a science, very little money going into that science right now, because people are pretty averse to thinking that we want to change how the Earth energy budget operates. We already intervene in putting greenhouse gases. Do you want to intervene in some other way? So those are, I mean, I don't know the answer to that, but I think that's the challenge here. Right?
That's fair. And then let me ask about the CDR, because it seems to be effective at the carbon, but I guess the common criticism of that is that it's missing all the other damages. So I wanted to get your thoughts about all the other ways we're polluting the planet that's not captured by CDR.
Yeah. So, I mean, CDR is only, so again, this is if you burn fossil fuels, carbon dioxide is one of your concerns. Fossil fuels, and let's say you burn coal, sulfur dioxide is huge. So, and ozone formation, NOx formation, they all help public health. There is an estimate that the number of people who died from pollution, air pollution last year alone could be in the millions, right? So there are other effects. It affects vegetation. There are a whole range of environmental impacts that are not just warming. So the CDR is only capturing the greenhouse gas and only carbon dioxide. And that would be an issue if you're not thinking a holistic view of these things and offering a kind of a solution that works in one way, right? This is the kind of a problem with technology is you have to think through the entire chain before you do something. And one of the things here is that the urgency that we need to implement something. And actually reducing the emissions is probably the most straightforward thing we can do.
Right.
Given all the other things. So what we focus is at the lab, in my group in particular, is to look at adaptation at various spatial scales. So the idea is that we want to calculate risk, and we want to adapt each of these different things to changes in climate. One is an installation scale, where we are talking about the entire installation. For example, say a power plant producing installation somewhere. The second thing is an infrastructure scale. And infrastructure could be like the urban transportation system in a city, or the local power grid and things like that, or the water, sewage water system in a city. And then the urban scale, the entire city as a whole. What does it have? What are the risks from climate to that location? And finally, you can also think of operation scale. So think of the electric grid that covers the East Coast or the Texas or the West Coast. So these are really larger things, and how would climate affect, and how would you adapt to the grid. There's a lot of work going on in California on how to adapt to impending climate change, whether you want to bury the wires underground and protect them from wildfires. These are large investments that people are talking about, and these are based on trying to understand some of the risk. Is the wildfire risk in California, for example, is going to increase in the future or decrease? And if it is increasing, which parts of the states will it be increasing? So we are doing some of this calculation. A lot of other people are also trying to help the utility industry understand where it may be more vulnerable and where it may be appropriate to take an adaptive action. So extreme weather, so this is a particular example of nuclear power. I've been working with the International Atomic Energy Agency recently, and kind of interesting just looking at a particular industry and how they are trying to think about how they should, or at least they think there are problems and they want to address those problems. So if you look at the nuclear power, nuclear power generates about 30% of the world energy, I think. In a state like Illinois, it's almost 60%. So it's a fairly large component in some parts of the country and the world, and some places like France is 70 to 80% is nuclear energy. Other places are completely coal. So, and they're talking about building, right? So there has been, but you think of nuclear power is not affected by anything, but they do get affected by weather. And if you look at the statistics for the last, maybe this is about 10 years, I think, the amount of disruption due to climate changes, the related issues like hurricanes, strong storms, ambient temperature change, water intake, and other things has been increasing in all over the world. For example, Western Europe in particular has been hit hard by a lot of these things. Like essentially what happens is that the temperature is higher and the water temperature also goes up. It's mostly cooling water. So they draw water in from a river or somewhere, try to cool the reactor and also throw the water out. But if the water of the intake increasing, then you have to have either take more water in, or you cannot actually, some places you cannot even operate, because you take the water in and you then expel the water out of your reactor. The temperature is so high it will kill the fish and other things living in the water, and they won't allow it. So there was a shutdown in, I think, somewhere in Europe because of this water issues. The other things are you if you think of Fukushima, it is also a combination of factors. One of them being this flooding. At a basic level, it's a flooding problem. They got flooded by various ways of water. So these are all kind of things that can affect. If you look at tropical storms that which is a threat to a lot of these nuclear reactors in other places, this is a tracks that are been up that is historical tracks of various regions seen in the world. Most of the reactors that we see in the world are actually in this tropical belt, so they really are interested in finding out what is going on. So climate change is making them bigger and more intense. The frequency of the storms actually landfall in North Atlantic storms, there is uncertainty on that. Intensity has been shown to increase. The size of the storms is also increasing. One of the things that is interesting is the translation speed, the repeat speed with which a hurricane that is a category 3 is going to category 5 is increasing rapidly, it seems like. But again, we need more data before we establish that. So drought and other frequencies also increasing. Drought frequency is also increasing. This is important for, it's again done in the context of nuclear power plants. I was talking essentially that you need to have water for cooling, because most of these things are water-cooled reactors. The climate change is all the relationship to flood is that the intensity of precipitation is changing across the world, and these are all the green places. Green boxes here show where the intensity of precipitation is increasing. That is, the amount of rainfall you get in an hour is increasing, and we are not actually set up to deal with that very well most of the world. So what are the approaches for estimating climate change risk? I mean, I'm not going to go through the whole thing. One is, if you are an installation, you want to adapt and you want to see what would happen to your site. If people use something called possible maximum precipitation, it is a kind of an old methodology. It assumes that the climate is kind of stationary in the sense that the extremes are not going to increase and the statistics are not changing. So it's based on historical understanding of climate, then you can calculate what would be the maximum amount of precipitation I can get on my site, given that this is what historically it was, but let me saturate the atmosphere and see how much more rain can I get so that I can prepare for flood events. So that is probably not very good idea right now, because most of the statistics are changing, and you cannot assume that you know actually what would be the maximum amount of precipitation you can hold, because the temperature of the atmosphere is increasing. When it increases, it holds more water, and you don't know how much it is going to increase in a given place. There's uncertainty on various levels of the atmosphere, how much temperature would go up. The other one is storyline approach. You take a historical storm and then put it in a future atmosphere, because you can do modeling. You can increase the temperature and other things and see what happens. And the third one is called downscaling, which is what we do. Downscaling is take a climate model, run it at a very high resolution to get a installation scale information, so you can assess some of the risks. So this is the one. So essentially downscaling refers to this process. You have a global model, global climate model, which operates around 100 kilometers by 100 kilometers. You take a portion of the global climate model and reduce it to regional scale. Essentially, it means that we cover the entire North American continent, and around, if it is doing at 100 by 100 kilometers, we can do the regional domain by 10 kilometers. You can go to local about 1 kilometer. So once you go into each of these scales, the computational cost burden actually remains about the same, but you are covering smaller and smaller regions. So this is the model we use. I don't want to go into the painful details of that. We use the computers at Argonne, which is, we used to have a computer called Mira, I still miss it. Wonderful machine. But right now we have this thing called Theta, which you use, and the Polaris, which we have started using. So we covered the entire North American continent as shown here at a resolution of about 12 kilometers. Resolution is like, think of it as a pixel in a picture. So you're solving a bunch of partial differential equations, and you have to discretize those equations. When you discretize, you're solving the equation at particular points on the map. So the distance between the points is 12 kilometers in the North American map on the left, and 4 kilometers on the right. So we are right now, we have done most of the analysis I shows the 12 kilometers. We are in the process of doing the 4 kilometers. So this produces huge amounts of data. For the 12 kilometer simulations I've shown there, about 1 petabyte, and it is for the 4 kilometers, we expect the data to be about 10 petabytes. So we are using a GPU version of the model as for the 4 kilometers. So I'll do a quick sciencey thing here. Please stop me if you think it's all boring. Bias metrics, when we talk about climate modeling or any modeling, we talk about bias. What is a bias? Bias means different things to different people. So bias doesn't mean that we are biasing the model to a particular result. It means that compared to observations, how does the model behave, right? Is it biased towards a higher than observations or lower than observation? So we are trying to understand at each grid cell, how is the model behaving? Is the model run warm everywhere, or is running cold everywhere? So that is the bias. So we do a lot of calculation to establish the model bias. And then the other thing we talk about is model uncertainty. This refers to numerical model forecast error due to complex nonlinear interactions in the model physics and model parameter uncertainty. Essentially, you are running a nonlinear physics model. There are a lot of uncertainties. So when you run a model at 100 kilometers or 10 kilometers, there are things happening within that 100 kilometer grid cell which you are not resolving. Essentially, what it means is that if you take a 100 kilometer cell, there's a whole bunch of things happening there, cars going around, trees and all. All this is parameterized into something that is one value for that grid cell. So for the 100 kilometers, you're using only a single value for someone. For example, clouds. If you think about clouds, the microphysics, the droplets in the cloud, they're much, much smaller than a 100 kilometer grid cell, right? So those are parameterized. So we call, there's uncertainty in how you parameterize them. So it's called parametric uncertainty. And then there is also nonlinearity in the physics itself that causes the solution to kind of meander a little bit before it settles to something. It's called internal variability of the model. So there is some variability within the model. And the third kind of thing, uncertainty we have is due to, in the climate model specifically, is emission uncertainty. So emission uncertainties are when you're projecting how much carbon dioxide will be there in 2100 or 2021, 2050, you are imagining how we live, right? Carbon dioxide and greenhouse gases are emissions are part of how we live and how we deal with fossil fuels. So if you keep driving the same cars, the same way of doing all the things, the carbon dioxide emissions will keep on increasing. But if we change some of these things, emissions will decrease. But we don't know how to forecast. I mean, we can kind of build scenarios, storylines, like let's say all the world does this, this must be the carbon dioxide emission. Let's say nobody does this, this can be the carbon dioxide. It's called business as usual scenarios, and the other ones are called some kind of mitigation strategies being allowed. There are 70 such scenarios. So that's the uncertainty over that range is quite large. I mean, if you do all the things that what everybody in the science community wants, we could have a temperature change about 0.5 to 1 degree. If you don't do any of these things, we could be having a 7 degree centigrade change by the end of the century. So that's a huge uncertainty cloud that hangs over this. And it's the only way to figure that out is to actually see how we are acting in terms of reducing uncertainty. So if you look at the whole model, yeah.
A question about first the model mechanics. So these are the North American, regional model. But first of all, around North America, do you have a standard? Which model are you using for the whole world as your boundary conditions?
Yeah. So for establishing the model bias and things like that, we use a what is known as reanalysis. Reanalysis is there is a whole bunch of reanalysis data that runs up WRF-5 and things. So this is the 12 kilometers was run by using NSAP. The 4 kilometers is run using WRF-5, which is from the European Weather Center. And for future forecasts and also historical, we also do time slices for the current and in the mid-century and end of the century, 20 years time slices. They use 3 climate models. They are called CESM, which is developed in US by NCAR. We used for the 12 kilometers, we used another model called GFDL, which was developed by NOAA. And then a third model is the HADGEM model, which is a UK model. The reason we picked these models for the 12 kilometer one, which is based on a set of calculations known as CMIP5, is that there is a parameter, there is a metric called climate sensitivity. So take any climate model, double the amount of carbon dioxide in it, and let it go to a steady state. Essentially, run it as long as it takes to, so you don't see more temperature change. All the models behave slightly differently in that. So the climate sensitive, the HADGEM model is very high. It gives you a temperature change about double the carbon dioxide, about 7 degrees. For example, CESM is somewhere in the middling range. It will give you around 4 degrees centigrade, right? GFDL is also around 3 degrees or something like that. So the reason we picked up this climate models is that we wanted to cover a range of sensitivities of the climate so that we are covering the uncertainty in models itself, model physics itself. So if you look at CMIP6, the range is slightly different. For CMIP, which is a 4 kilometer, we are using a different set of models. We are using a model called ECAM, which is in Europe, which is also a European model, and then the CESM model and the HADGEM model. So we dropped the GFD model, which looks very similar to CESM. Yeah.
So maybe I didn't understand. I thought you were saying, are these for the boundary conditions for your model, or are you using WRF for North America, or are these models your workhorse models?
Yeah, so they are the models. The models that I mentioned right now are for the boundary conditions, and the work model then takes those model from the global model and downscales it to North America.
Okay, so then a good question is, what I thought WRF was much smaller than North America, because that seems like the boundary between weather and climate is starting to get blurred at this point.
Yeah, I mean, it's you don't want to. So WRF is a model that you can run for the pretty much. You don't want to run for the entire planet. You can learn for the northern hemisphere or southern hemisphere. It's a hemispheric version of the model. You can run it, right? The only thing is, if you run a model like that for the entire larger and larger domains, it becomes more and more expensive because of the number. So, for example, for the 4 kilometer simulation we are doing, which covers from Alaska all the way to Puerto Rico, the number of grid cells are about 200 million grid cells. And you were doing at 4 kilometers, you're doing a calculation every less than a second. So that's a super duper expensive calculation. So that the forecast model, the weather forecast model you see on a TV in the night is also run over most of North America. It actually is a fairly large domain. It's called HER model that you see on the TV. It has a domain that goes all the way into Canada and covers most of the US. So it's run on a continental scale. So people run it on a very local scale too, but so the reason we don't run on a local scale is that the boundaries affect your solution very quickly. But when you take a domain really large, you're only seeing the effects of synoptic scale. So you have to keep it, when you're thinking about this as a climate problem, you have to make the domain really large so that you're not just interpolating the boundary condition to a local domain, so that you can physics in the model develop, and also you can change the sea surface temperatures and other things as climate changes.
And if I wanted to do like the next level of downscaling, like for a state or a particular city, like New York resilience, how challenging is it to start like hierarchically downscaling?
So the calibration we've shown covers all over the continent. So it is already fairly high resolution. So if let's say you want to go to 1 kilometer in a small region.
Exactly. Yes.
So you can take the output from something like ours and run it. How complex would it be? The calculation for somebody statewide should not be that painful. I'm assuming a grid cell would be probably in the 50 million grid cell count. So it should be fairly, you should be able to do it on a decent computer, not on your laptop.
Right. Now, one more thing, you were talking about the drivers of emissions. Are you working with like the integrated assessment models like GCAM and a bunch of others that try to have, I mean, they have a weaker model of the climate than what you have, but they do have a lot of the industrial societal responses to various climates.
Yeah, I mean, I don't do that. It's almost an entire field of study. So they're
yes, it is.
There are different ways of different policy instruments and things like that. You need to be a little bit of an economist, or actually an economist, to figure that out. I don't work with that. We do right now trying to figure out. So the way the climate model in something like a GCAM or any other integrated model is called a reduced error model. Essentially, it's somewhat reduced. It is one of the challenges of that doing that has been when you reduce define the physics lower, they also use very coarse grade actually. Used to be, now they're trying to get higher grade. But if the cost, as it becomes higher and higher resolution, it actually becomes more and more expensive. It becomes more and more becoming the climate model. So how do you reduce the cost of this region reduce our models? One of the solutions seems to be maybe building a machine learning model for this reduce our model. So that's one of the things we are working on.
That makes sense. Yeah, and then they would benefit from your accuracy. And then maybe one more thing on this. So by the time you start getting to these localized impacts, you can start doing things like you emitted so much, so it caused a flood in my city. It's your fault. It's a difficult, attribution to make. But how far away are we from making, like, even attempting such things?
Yeah. So if you look at any climate disaster right now, there is immediately a paper within 3 months by a group in Australia which does this climate attribution studies. The way they're doing it is they take the climate, they say no carbon dioxide, put carbon dioxide here, put carbon dioxide there. They've created an ensemble of 20, 30 member simulations. And then they say there's a 30% likelihood that this event happened because of anthropogenic emissions. They don't say from where, but they say that.
Yeah.
So this has been, there are 2 or 3 groups doing that right now. So there is some value to that, but I think overall, on a broader sense, we know this is being driven by climate change. At this point, it's what do we do about it kind of thing, right? So yeah, the attribution of a single source to an effect, we are a little bit further away from that. I mean, I would say so one challenge is that is 30-member ensemble really a great number to look at uncertainty. In my opinion, it's not. It's only looking at a fixed set of parameters. You actually need to run a huge 100,000 member ensembles to actually capture the uncertainty for all the things that are going on in the globe, right? So we are not anywhere close to doing those kinds of calculations, and that's why I'm kind of interested in this machine learning models, because potentially right now these models are running up to factor 10 faster, maybe even faster, right? Some of them are look like possibilities that they could be 100 times. So if you can run 20 member ensemble simulation right now, if you can do this reduce R models with our, let's even not call it a reducer, let's call an emulator. Emulator for all the glory of the physics, all the glorious things that this high resolution models can do. And you can run it 10 to 100 times faster. Then instead of doing 20 member ensembles, I can do at least 200 ensembles or 2000 ensembles. I think this is a way for reducing uncertainty and projections and a lot of the impacts that we see right now. And maybe, and the idea is you don't want to coarsen the model to get to this larger number of ensembles. You want to keep the resolution high. You want to capture all the effects and then go to this ensemble. So that's my hope. We are working on it, or a number of people are working on it, but hopefully we'll figure this out pretty quickly.
Awesome, thank you.
Yep. So this is a kind of a bias chart which we make, not very important here, but just to say that all the models have different ways of, for each of the regions. These are all, if you look at my y-axis, these are all the different models that we have run and different ways of running the same model that I've described before. So at CESM, the idea is that if you look at HydGem, that is a model that from which I downscaled to the 12 kilometers. GFDL is the one model. GFDL is a global model, and then downscale it to 12 kilometers. I nudged the model with the GFDL simulation. I don't nudge it. I bias correct it. I don't bias correct it. So we have all these ensembles. There are about 8 ensemble members for each of these calculations. So we can see where does these models in general do well and where they don't do well. So when I looking at talking to somebody and I'm saying we are predicting a 2-degree temperature change, we are projecting a 2-degree temperature change over some part of Illinois or California, you can say that the model has a cold bias here of 0.5 degree. So then you can make a better decision on how you should look at this number. So we do a lot of this preparation of the historical evaluation of the data set, so we can talk about this much. So these are the projections. We probably guys have seen a lot of them. Essentially, it says that by the end and middle of the century, you can have a number of heat waves. This is the 3-day heat wave that is defined by NOAA as exceeding 95% the historical threshold. So if you go all the way to the right and all the way to the bottom, you can see this could be about 18 to 20 heat waves in large part of the West and even in the Midwest. So that's an amazing thing to keep in mind as we look at these things, that you could have an entire month which will be warmer than what we are right now. The highest temperature, the maximum temperature you use for 3 days, that could last more than a month in the future. So that's one of the things. And the intensity of precipitation, we do look at it very carefully. What our theory right now, hypothesis is that the intensity of precipitation, which is one of the most remarkable things, or one of the things that you can observe all over the Midwest, East Coast, and even some parts in the West, is that the intensity of precipitation, the amount of water you get in an hour, has increased tremendously over the last 20 to 30 years. That's one of the indisputable facts of the changing climate. Why does this happen? Maybe the water, when they increase the temperature, it holds more water vapor, so you're getting more water dumped in it. But it also looks like the size of the storms is actually decreasing, and the decreasing size actually leads to a more intense precipitation in a smaller area. So this is some of the proof for that we have done over the last few years. As I said before, our interest is looking at extremes. So why do we look at extremes? The idea behind looking at risk is that, so when you talk about risk is related to an extreme event. So we want to model the extreme events as best as we can. So Why do you want to do that? Then we can predict what is in a 1 in a 50-year event is, what is 1 in a 100-year event is, what. So that is the statistic people use to understand how you cope with the risk. It says you will have a storm that increases the water depth by 10 feet every once in a 50 years or once in a 100 years. You know how to build whatever you're building to that specification. So it's a very important number. We use something known as generalized extreme value to do that. I'm getting pretty close to ending the talk, I think. Uncertainty, so we do a lot of uncertainty analysis. If you look at the figure here, it shows the 95% uncertainty band for on the right. So you predict what the temperature would be and all what the change would be, and also you want to predict the uncertainty on that. So we build a whole bunch of scenarios for a given thing. For example, this is just shows for wind. We have a sample set of 50 or so simulations, and then from that we subsample using something like this. So we can build a PDF of the expected change and also the uncertainty with the change. So you can look at what is a once in a 50-year event. If you look all the way to the right, the 95th percentile event will have so much uncertainty. So we also look for projections of we can convert the simulations we are doing into water depths and water stream flows. This looks like the stream flows for how would the stream flows on the Northeast change as because of climate change. And it shows what the median flow would be compared to right now, and what the lowest and the highest 95th percentile, for example, will change as you go into the forward, and how the return period, like if you look at a once in a 50-year event, it shows that the flows will be in the 95th percentile. It shows the red lines are the flows at the 95th percentile. And also it shows the uncertainty. Most of the stream flows are, as I shown here, are increasing as we go into the forward, some not so much, some are higher. Here we show a kind of once in a 50-year inland flood looks like in the Northeast. What will the water depth be? So we can do this calculation. These calculations are done actually at a resolution of about 200 meters per grid cell. So for the entire Northeast, we do a 200 meter per grid cell simulation. We are covering the same simulation for the entire continental US at 200-meter resolutions. We are almost close to completing those calculations. And that will give you a risk of change in flooding depth as we go into the future, given a scenario. So you can do at a high emission scenario and a mid emission scenario. So this is kind of, again, trying to figure out what is the risk. What is the once in a 50-year flood is 8 feet right now. Will it be 15 feet in the future or 0 feet in the future? So what is uncertainty in what these guys are estimating? So these are the kinds of things we can provide. So we also look at coastal projections. This is a model called EarthCirc, and it looks at what happens when you have a hurricane. One of the biggest things on a hurricane is actually how much water comes on land and where it gets flooded. So this is about a 90-meter resolution model, looks along the coastal of the US, and this actually shows an example of Manhattan for two things. One assumes that there is a median sea level rise, which is, I forget, half a feet, I think, by 2054, and the other one, which is a maximum higher sea level rise. Again, I don't exactly remember what that is. It shows you what the storm surge and extreme flooding risk will be from a once in a 50-year or various parts of Manhattan. We did this for some power company. They are trying to see what risk their exact facility is experiencing. We can go to this map is shown at the course level because they don't want us, the other plot is with them. So you can go almost to the side to the 90-meter scale and see how the risk will change. So just from the hurricanes, you can also calculate what in a, for example, a 1,000-year risk is for the return period, what would be the depth of water you can. These are important for some things like nuclear reactors. Nuclear reactors, guys, want everything to be calculate risk in the once in a 1,000-year event because they want to be extremely careful how they build that. We also look at nor'easters and how nor'easters are going to change in the future. We predict that our model are projecting that nor'easters actually move more inland. So the flooding risk from them could actually decrease, except for Delaware Bay, where it could be higher. We also do droughts. And one of the interesting things is that if you look at the drought projection for the US, if you look at all the way to the bottom, the 95th percentile and once in a 50-year risk, a large portion of the US, mid-part portion of the US, and the western portion of the US actually have a much increased risk of drought. And this is important for people who are trying to planning. because drought risk also goes along with the wildfire risk. This is the wildfire risk map, and again, you go all the way down, you can see that there's a large portion of the country that the wildfire risk, especially in the Midwest, it's going to be a higher risk for wildfire, not just the West as we see right now. So these are important things. If you are trying to adapt or build infrastructures to withstand all these things, you have to keep these things in mind. You can also look at things like crop, how they typically all the crop yields decrease as a result of temperature, but it doesn't take into consideration that you may have a better seed that can withstand higher temperature. Right now, we are doing at 4 kilometers. That is the plot all the way to the left, compared to around 12 kilometers, which is in the middle, which we have right now. The idea is that we are actually focused on risk. If you want to do risk, then the idea is to capture the extreme events as best as we can. So we go to this scale called convection resolve, which is 4 kilometers. And this is the simulations we are running right now. There's a 20-year bunch of simulation for mid and end of the century and historical, and see. And when you run the simulations, you can see the storms in them. So each is a capture of a 5-day event from one of those storms. Actually, I think this is Hurricane Ida. So other things we are looking at is there's a project called Crocus, which we are looking at Chicago itself and looking at various neighborhood scale changes that can happen in Chicago and how the local communities could potentially adapt to this oncoming changes. So it's looking at really micro scale on heat vulnerabilities and expected changes. What could you do? Could you build a cooler roof, decrease AC consumption, or a green roof? So these are the kinds of solutions we are trying to figure out. These models actually are very, very high resolution models. We are working at street scale. The idea is if you plant a tree that is cool, does that cool that particular street and that particular block. So we have trees and things like that in the model. These are computational fluid dynamics model and run for a couple of days. They are not meant to be doing climate scale simulation. So real world applications, as I said, we work with a lot of utility companies. These are heating degrees days, the number of days you actually need to heat your house. They seem to be decreasing all across the Midwest. This is done for a company called Comet, which provides power supply to us. And this is cooling degrees days, number of days you actually need to cool your house during summer, and they can seem to increase. We also, as the calculations I've shown before, helping New York Power Authority, for example, imagine what the stream flows will change and how they can adapt to oncoming changes. So this is my team. There, some of the people, a whole lot of people work on it. Just want to acknowledge all of them. Jelly Wang did most of the 12-kilometer one. Chen and Jiang is doing the 4 kilometers work. And Tom Wall is an engineer who's working with utilities and sector people. Yep, I'll stop there. And we have a data portal called CLIMR, CLIMRR, and this is funded by FEMA, the Federal Emergency Management Agency, and AT&T. And you can go to this website to obtain data. Some of the data is there. We are trying to populate as much as we can. Thanks.
Well, yeah, thank you very much. This is fascinating. I guess the big question is, so you're providing the information about what will, who will be affected, how, and some about what we might be able to do about it. I guess, how is this flowing to stakeholders? I mean, might be investment companies that want to protect their assets, or investment companies that want to not invest in vulnerable assets, or municipal governments that want to plan their, their activities. Like, how's the translation going?
Yeah, so we work with a lot of private sector, a lot is loaded word. We work with a few private sector companies, mostly in the utility sector, because we are from Department of Energy and we are closely connected to them. And so the challenge is we call it translation. So I have all this information. How does it translate to somebody who wants to use it? Let's say I say the temperature increases by 2 degrees. Why should I care? Right? I mean, what does it mean to me? So that's why we're looking at cooling degree days and warming degrees. The idea is to convert that into a number that the utility can understand and say that maybe the load will increase by X% by the future. So how do I go about if I'm constructing something? How do I go about it? One of the comment guys told me that For example, one of the things they found it really helpful in the calculation is typically we expect the temperature to be higher in the Chicago region. They build all these instrument hubs where now they think there may be a need for air conditioning in the future because the temperature will be warmer by a lot compared to now. So that's an adaptation strategy that they are thinking about. AT&T, when we work with the company, AT&T Fiber, so they are thinking about where do their data centers have the most vulnerable and what can they do about it, right? What if there's a flooding in a particular place, will that affect my data center? Will it affect my fiber that I'm burying underground, all these places? So they are looking at it, but the interesting thing is, because I'm not on the other side, somebody who does the calculation, I keep asking them, can you tell me what the spreadsheet looks like and where this number goes as far as the risk goes? I think that's an interesting part, and that's actually pretty challenging. I mean, maybe the guys who are doing it understand better than me, but I don't have a good feeling about it. But we constantly are educating them. We are giving the data. So some of the things like flooding data. Why did I start doing flooding data? Because that's the most interesting thing for a lot of these people. They are not interested in intensity of precipitation changes by 10%. The question is, why do I care? They care because they are interested in flooding, right? We talk to them for months and months and finally figure out, okay, they are interested more in inland flooding or coastal flooding rather than just knowing the intensity. So we start doing this impact kind of. So that's how it's been evolving. It's an interesting process, but I think a lot more people are aware of this, that they need to take climate risk into consideration when they are building. They're seeking out people like us to figure out how to do that. And I think it is slowly changing. So people know. The only thing is whether I just need a number to put in my annual report, or do I want to do this in a sincere way so that I'm actually addressing the problem, right? So those are the kinds of things that are still a question. I see a lot of people just use some random number. I mean, I haven't said random numbers. Something simple. Just say that, oh yeah, we are safe, and then
right. And maybe the last one. There's a lot of work now on computing the social cost of carbon, which is mostly about the downstream impacts, and a lot of it is more econometric analysis of whenever something gets hotter, then so many more mortalities. But your predictions seem, I mean, they're not quite in the human space, but they capture a lot of the drivers of human suffering. So I guess what do you see your role in computing such human impacts?
So the one example, recently we got funded with this project called CROCUS, which stands for Community Research on Climate Urban Systems or something like that. It's funded by DOE. It's a very large project. We have 12 partners. And what we did for this project is that before we even wrote the proposal, we talked to a lot of communities around Chicago, trying to find out what they think of climate, what do they think climate will do to their neighborhoods. So they are partners. They actually partnered with us when we wrote the proposal. So we are trying to address some of these kind of impacts to the community at that scale, at the community scale, trying to figure out if the temperature in this microclimate is going to be 5 degrees warmer or 2 degrees warmer, what kind of adaptation do you need and done, and how would you? I mean, we cannot tell them what to build. We can tell them this could be this, and green roofs may be a better solution than a solar roof. So those kinds of things are what we could do as a part of CROCUS. As a person who works with Department of Energy, we don't recommend policies. We are government, quasi-government. So it's not our response, not in our job description to tell people what the policy should be. We do the calculations. We support the communities, giving them technical information on what they can expect, what is the best solution will be, and they take the decision on how they should proceed.
Got it. All right. Well, yeah. Thank you very much. It was fascinating.
Thank you.
Yeah. Have a great rest of your day.
Yep. Thanks. Bye.
Bye.